A lighter, solid sphere will always outpace a heavy, hollow ring down an incline. This happens because rotational motion follows a specific framework that runs parallel to the standard laws of linear mechanics. This table provides the mapping between the two regimes. Force correlates to torque. Mass translates to moment of inertia. Linear velocity corresponds to angular velocity, and momentum maps to angular momentum. Using these variables allows us to analyze complex rotating systems by applying the same logical structures we use in linear physics. This diagram shows how torque functions as a cross product. The turning effect is maximized when the force is applied perfectly perpendicular to the lever arm, whereas a parallel force provides zero rotational acceleration. We find the direction of that torque vector using the right-hand rule. Align your fingers with the wrench, curl them toward the force vector, and your thumb indicates the resulting axis of rotation. This vertical vector represents the torque required to change the angular velocity of the bolt. In every rotational problem, the geometric angle of the force is as significant to the outcome as the magnitude of the force itself. Rotational resistance, or moment of inertia, depends on the location of mass relative to the axis of rotation. These standard formulas show how shifting that distribution changes an object's resistance to spinning. Correctly calculating these values off-axis requires a strict distinction between 2D and 3D geometries. Flat 2D laminas allow for the use of either the perpendicular or parallel axis theorems. However, for 3D objects, the parallel axis theorem is the only valid tool for finding the moment of inertia about a new axis. Combining this inertia with angular velocity gives us the total angular momentum of the system. When the net external torque is zero, that momentum is conserved. This blurred figure skater achieves a higher spin rate by pulling her arms inward, reducing her mass distribution and forcing her angular velocity to rise. Manipulating the distribution of mass is the mechanism the physical universe uses to conserve energy when the dimensions of a rotating body change. Rolling motion has two simultaneous components: linear translation of the center and pure rotation. In perfect non-slip rolling, backward rotational velocity at the base exactly cancels forward linear velocity, resulting in the contact point having zero instantaneous velocity. A rolling object possesses dual kinetic energy, requiring us to sum the energy of its forward motion and the energy of its spin. To solve for the velocity of this 5-kilogram solid cylinder on a 2-meter incline, substitute its specific moment of inertia into this conservation equation. Pause the video now to find the value of V. The starting potential energy is distributed between two sinks, a linear speed of the cylinder and the rotational kinetic energy of its mass. Base velocity is 5.1 meters per second. Mass and radius squared terms cancel, isolating the inertia fraction. This explains the race. The solid sphere's fraction is 2/5, the ring's is 1. Requiring less rotational energy, the sphere retains more translational speed. Mastering this chapter involves mapping linear rules to rotational counterparts, selecting correct inertia formulas, and calculating how kinetic energy partitions between motion and spin.